Right everyone, hi. This is second video uh, on modeling in M1. So we've done a lot of kind of theory in video 1, so now we're just going to push right for it, kind of revise where we were. So we've got a particle, scenario 4, mass 3 kilograms, held in equilibrium by a horizontal force on a smooth slope. Okay, so we've got a slope, we've got our mass. Remember, weight's always going down. We got a normal reaction because the force is always perpendicular to the surface this is resting on. It's in equilibrium, so there's no acceleration. It's being held in equilibrium by a horizontal force on a smooth slope at 25 degrees. So as soon as I've seen the slope, I would split my weight. Actually, let's not do that yet. Okay. Normally I would split my weight into components, but first I just want to get all the forces I know down, and then I can decide what's the smartest move to do. So as this thing is smooth, if basically I need to ascertain which way this horizontal force is. Is it left or is it right? Well, it's got to be left. It's got to be going right, sorry, because if this thing's smooth, and if I just drop the particle in it, let's say a marble down a slope, it's just going to fall down the slope, isn't it? So the horizontal force here has to be acting that way. Okay, that's helpful. So like I said before, let's say I was trying to find out what this horizontal force is, let's call it P, right? I could split the weight up into components. So what I could do is split the weight up like this, like we did before. So now you've got your normal reaction, you've got the force there, you've got the force there, but I'd also, because remember, you're always going to resolve either perpendicular to the slope or parallel to the slope, but it doesn't have to be perpendicular parallel. All it means is that I'm resolving 90 degrees to each other, okay? So I could resolve in the direction of the normal reaction, and therefore I would have to resolve in the other way, going parallel to the slope, down towards the slope. Or I can be intelligent about it and with a bit of savviness. So, by the way, if I did that, I'd have my weight like that, but then also what I'm saying is that my P would have corresponding forces like so, wouldn't it? So you've always got your right angle triangle, but we wouldn't denote that triangle like that. We would have the force going out of it. So normally the force would go out of it like that. That's P's parallel to the slope force. But also, because you notice this vector is going, if I draw this vector this way, it's got an across element going down like that, and a parallel element, doesn't it? So there's my parallel element to the slope. And it's also got this downward element here perpendicular to the slope. So that would be another one here, right? So this one, as it would be next to the vector here, so 25 degrees would be here. Therefore, this thing would be next to, so therefore this would be P cos 25, and this one going down would be P sine 25. But that's just so much more work if I work stuff out that way. If it's a bit confusing, don't worry. Like I say, everything will come eventually. So let's do it again, but let's do it smarter. So I've got 3g going down, normal reaction, always the same, horizontal force like that. At the moment, the horizontal force, P, and the weight are 90 degrees to each other already. So Newton's second law, I might as well resolve left and right and up and down, like normal. The only problem is, I said all forces need to be accounted for, and this normal reaction is not left, right, or up and down, but you can split it up into components. It has an up and down force, and it has a left and right force. So its force going left is going to be here, isn't it? Because remember, it started from this triangle up here, but we don't normally draw the triangle. We know this is 25 degrees. The force next to the angle is 25 degrees, so therefore that is going to be r cos 25, and the other one is going to be r sine 25. So if we resolve left, right, what's our force going right? Well, it's P. What's our force going left? Well, that's r sine 25. It's in equilibrium, so our MA equals 0. So therefore P equals r sine 25. But we don't know what r is yet. So let's resolve up, down this time. So up, down, we've got all the forces going up is r cos 25 minus the forces going down, that's 3g, equals, again, it's in equilibrium, so 0. So we know that r equals 3g, moving that over cos 25, and therefore summing that into P is 3g over cos 25, all times by sine 25, which equals, and remember, g is 9.8, so 3 times 9.8 divided by cos 25 times by sine 25. So it's 13.7 newtons to 3 SF. Okay. All you need to get then is how to split forces into components so you're resolving perpendicular to each other. Okay? You will get this. Okay. Now we've got other scenarios such as connected particles. So that was what we've just done is single particles. But now we're going to deal with connected particles. So when two particles are connected to each other. So let's draw the situation. So two particles, P and Q. So here's P, little circle around it. Here's Q, little circle around it. A massive 5 kg and 3 kg. So there's 5g. And here's 3g. Are connected by a light inextensible string. So light means zero mass. So in other words, you don't have to take into account the weight of the string. And inextensible means doesn't stretch. So it's a modeling assumption that we make in M1 and M2. It's not until M3 that you have a stretchy string. Okay? If it's an inextensible string, it doesn't stretch, and therefore the acceleration remains constant all along the whole length of the string. Okay? So, particle P is pulled by a horizontal force of 40 newtons. So particle P is 40 newtons that way. It's connected by a light inextensible string. So there's the string. And let's think about that string. And we're thinking about that in a sec. Particle P is pulled by a horizontal force of 40 along a rough horizontal plane. So a rough floor, which therefore means you've got a normal reaction at P and a normal reaction at Q. That's why I'm calling it RP and RQ subscript, because they're not going to have the same normal reaction. And there's going to be a frictional force at P, right, which is going to be our mu r, but it's telling us the coefficient of friction is 0.2. So 0.2 RP, and the friction here, remember, it's going opposite to motion, so the friction here is 0.2 RQ. Okay? And the string, let's talk about forces on that string then. So that string is being pulled, yanked, by the 40 newtons, but it's also got these two particles attached between either end. So once RP or P starts moving, this string goes tight, doesn't it? And then the string itself is trying to keep itself together. There has to be forces acting within the string. The string's trying to keep itself together, whereas the two particles are trying to stay where they are. So if one of the particles is moving, the string is trying to keep together, which is where it has tension then. So tension is when the string is trying to keep itself together, keep it towards the middle without, so it doesn't stretch and break, right? So tension, you've got this little dotted line, always goes towards the center, okay, between the two particles. So I've now modeled this situation, and we can find certain things with it now. And as it's being pulled by 40 newtons, I'm going to assume it's accelerating that way. Notice the double label again. Okay, so how do we do this? It's the same thing. Let's try and find our unknowns then. So Newton's second law, F equals ma. We'll resolve up first, okay? If I look at the forces just at P, so just look at P only. I'm only interested in the particle P at the moment. If I was, so at P, right? You can see that RP is going up, 5G is going down. It's not accelerating up and down, so therefore it's in equilibrium up and down. So therefore we can say that RP equals 5G. Okay, likewise at Q, up and down, RP must equal 3G because there are no other forces acting up and down. That's helpful, okay? And that means we know what friction is here and we know what friction is here. Let's now move to the right. Sorry, move to the left because that's where we're accelerating. So let's think about it. I've got a whole system moving here. The whole thing is moving. It's almost moving like one particle, isn't it? Because this entire, you could look at it like a chassis is moving to the left. So the whole thing is being pulled at 40 newtons, isn't it? Even though P is being pulled, that string is kind of like a pole. It's pulling the other one along with it. So 40 to the left. Anything else going to the left? Well, you've got that tension here, don't we? Anything going to the right? Well, yeah, you've got the other tension. So can you see the two tensions cancel out? So you don't need to consider them because it's all put within one system, right? The tensions cancel each other out because they're in equilibrium trying to go towards the middle, okay? So 40 going to the left. Anything going to the right? Yes. 0.2 RP, so the friction, 0.2 RQ equals total mass. So what is that force 40 is pulling 5G, but it's also pulling 5 kilograms, but it's also pulling the 3 along with it. So the total mass is 8 kilograms times by the acceleration, okay? And we know what RP is, we just worked it out. So that's 3G minus 0.2 RQ, which is 5G, all over 8 is the acceleration, because I just divided everything by 8, right? So A equals, let's have a look, 40, subtract 0.2 times 3.9.8, minus 0.2 times 5 times 9.8, all divided by 8. So 3.04 meters per second squared to 3SF because we're dealing with G. What if the question said find tension though? So we found acceleration. What happens if the question said, so part B, that was part A, find tension. What is the tension in the string? How do we do that? Well, tension, like we say, because it's an inextensible string, is even throughout the entire string. You notice that when we took everything going to the left, the tensions cancelled out, didn't it? So all I can do is take one particle by itself, because tension's going to be the same if I take it at P or at Q. It literally doesn't matter. So I'm going to take it at P, and because it's moving left or accelerating left, I'm going to resolve left. And notice it's very important I'm saying at P. So at P, what forces are acting on P? So 40 going to the left, because I'm only concerned with what's happening to this particle because the tension's going to be the same as what's happening at this particle. So that's why I can split it up. That's why I put that dotted line on straight away at the start. So 40 is going to the left. What's going to the right? Well, tension's going to the right. Notice it doesn't get cancelled out this time because I've isolated that particle. And also the friction, 0.2 rp is going to the right, equals the mass times acceleration. The mass is 5, the acceleration we just worked out was 3.04. So therefore, tension equals 40, subtract 0.2 rp, which is 5g, minus 5 times 3.04. So tension equals 40 minus 0.2 times 5.9.8 minus 5, 3.04, 15 newtons. And again, that's 2SF because of G, okay? If you did it on the other side, at Q, you'd get 15 newtons as well. It literally doesn't matter. You don't believe me, do you? Okay, fine, fine, fine. We'll prove it. Again, going left this time, then at Q. Let's pretend we're just doing it at Q. I'm only going to do this once to illustrate it. Force is going left because it's accelerating left. Tension's going left. Opposing force is our friction, equals our mass, which is 3, times our acceleration, 3.04. So therefore tension is 3.04 plus 0.2 RQ, which is 5G, and therefore tension equals 3 times 3.04 plus 0.2 times 5 times 9.8. Right, yeah, it would have worked if I'd written the correct weight down. So the reaction at Q, sorry, that should say Q, is 3G, not 5G, and therefore we do get the 15 to 2SF. Okay, cool. Brilliant. What's next? Okay. Final one then, of connected particles for now. Particle P and Q of mass 2 and 3 m are attached to this. Okay, so particle P, here's a pulley, right? Particle P is here, there's P, and there's Q. So are attached to the ends of a light and extensible string. The string passes over a small smooth pulley, and this is a fixed pulley, right? So you could put that like that. And this is the pulley P. I could write pulley. And it's smooth, that's interesting, so it's frictionless, so you don't have to worry about the string slowing down at certain points and things like that. And the fact that it's a light string means it's zero mass, and inextensible means acceleration is going to be uniform throughout, okay? And the mass is hanging with the string taut. The system is released from rest. So P has mass 2, I think it should say 2m. So 2m, and Q has 3m, and like I say, weight always acts down, so this would be 2mg and 3mg. I remember, as we're talking about a string, this string is trying to keep itself together. So careful with this system, this tension system, all right? That's significant if you want to isolate particles. But remember, the tensions cancel each other out when you take a whole system, right? The string is released from rest. So let's say we want to find acceleration. So let's think about that. If we release both these particles from rest, what's going to happen? Well, Q is going to race down, isn't it? It's going to accelerate down, and at the same, because it's heavier. Whereas P is going to race up with the same magnitude of acceleration. So let's use Newton's second law again, and let's resolve down, because our direction of motion in the end is going to be down, okay? What forces are going down in the direction of the acceleration? Well, 3mg is going down, but at the same time, 2mg is going up, isn't it? It's going up, and therefore the 3mg on this side has to deal with the weight of p on the other side. So actually, this is trying to slow it down. You've got two forces acting in opposite directions, really, because this one has to fight against this one. So 3mg going down minus 2mg equals total mass, because we're talking about the whole mass of the system moving, which is 5m, all times a. So 3mg minus 2mg is mg equals 5ma. So therefore divide everything by m, the m's cancel, and a equals g over 5. And g over 5, 9.8 divided by 5 is 1.96 meters per second squared. Now, if you're really not sure why that works, you know, that's done basically. If you wanted to find tension, so now I want to find tension, let's say. Again, I have to isolate one of the particles because these cancel out otherwise. So I'm going to isolate, literally doesn't matter, I'm going to isolate Q because it's accelerating downwards. I've got a force 3mg. What's opposing it? Well, T is opposing it. Equals the mass 3m times by my acceleration, which I know is 1.96. So therefore T equals 3mg, subtract 3m, 1.96. Which is going to be 3 times 9.8 minus 3 times 1.96. So 23.5 m to 3sf. Okay. I think that's it for now. If you're really curious, so you could start the tape now if you're not curious. If you are curious, why does that thing work? Because the logic doesn't quite follow. Well, really, it's doing a simultaneous equation kind of in your head, or just like skipping a step, really. Because the tensions cancel each other out, I could do exactly what I just did. So if this was part A, finding the acceleration, this was part B, I'll just go back to part A again. I'd have to isolate the two particles, basically. So at P, resolving up because it's accelerating up, force is going up at tension, minus the weight equals the mass times acceleration, right? And at Q, like what we just did, resolving down, we would have 3mg subtract T equals 3ma. Can you see we've got a simultaneous equation there? That if we plus these together, T minus T disappears, we get 3mg take 2mg equals 5ma. So that's where that logic up here came from, in case you're wondering, but it's absolutely fine to just skip to this logic here if you understand that. Okay.